3.1, solve linear equations by graphing, or linear systems by graphing. So, as I'm sure you can guess, we'll be graphing in this section. So we can have exactly one solution. We can have infinitely many solutions, which just means it's the same line. Or we can have no solution, which basically just means there's parallel lines that aren't going to intersect. If it is consistent, there is at least one solution. If it's inconsistent, there's no solution. Independent is exactly one solution, and dependent is infinitely many solutions. So those are going to be the keywords that we need for this section. So I'm going to, I don't remember how to do it. Nope, that wasn't it. Put some graph paper up here. This is one section where I would say it's probably more beneficial to have graph paper, because when you're trying to figure out where the point of intersection on your graph is, unless you are really, really good at guessing, your point is probably going to be off a little bit. So, number 4, these say to graph the linear system and estimate the solution and then check the solution algebraically. So basically just plug it back in and make sure that it works in the equation. So starting out with an easy one, y equals 5x plus 2 and y equals 3x.
We're on our PSAT, but I didn't know how to do it.
I would do this algebraically typically. I don't usually do the graphing method. But this says we have to graph, so we're going to graph. Did it say you had, well, you couldn't have had to do it by graphing because it was multiple choice.
We were placing.
No, there was like
It was those
10
equations
fill in
at
the
the top.
blanks, and I was like, who did this?
Fill in the blanks on a PSAT.
Yes, it was terrible.
I didn't even know that was a thing. All right, so we graph each line individually. So y equals 5x plus 2. So at 2. And then up 1, 2, 3, 4, 5 over 1. 2. So that's my first line. The other one has an intercept at 0. And then up 3 over 1, down 3, back 1. That's not 3, that's 2. 1, 2, 3. There we go. And so sometimes you need to go like, you know, typically with a positive slope, our tendency is to go up and right or whatever. But sometimes we actually need to go down and back in order to get that point of intersection. So this point here would be the point -1, -3. And so then we plug it back in to check. So I'm going to plug it into the bottom one. So -3 is equal to 3 times -1. -3 equals -3. So we're good. Technically, you should really check it in both, but I'm only going to make you check it in one of them. 10. Y equals -3x minus 13. And -x minus 2y equals -4. So sometimes they don't give them to you already in slope-intercept form, so we need to change them. So I'm going to move this over. So -2y is equal to x minus 4 divided by 2. So y equals -1/2 x plus 2. So then, because this one's going to take a lot of space, I'm going to do it over here. I think I'm going to count by 2s because this is going to be Just keep in mind if you do count by twos, that's what you're doing, so it doesn't get confusing. And I would count by twos like in both directions, and not just like on the X or just the Y. I would do it on X and Y. So I'm just gonna note here that I'm counting by twos so that I know. All right, so the first one, intercept at negative 13. And then I can go down 3, right 1, or I can go up 3, back 1. And only because I've done this problem before, I know that I'm going to need to go way up here, so I'm going to keep going. But you wouldn't necessarily know that with what you're doing. I'm going to pause there for a second. I'm not going to draw the line yet, though, because I know I'm going to have to go farther than that. And then the other one, intercept at 2. And then down 1, right 2. Or up 1, back 2. All right, I'm going to pause there for a second, and then I'm going to keep going with the blue ones. So what was that? Up 3, back 1. Okay. So, not perfect, but as close as it's going to get, more than likely. All right, so approximately we're intersecting somewhere in here. It's not lined up perfectly, but about what would that point be?
3, 3, or negative 3.
Keep in mind I counted by twos.
6.
Oh,
Negative 6.
Negative 6.
7.
Sure.
Negative 6.
-6, -7 would be down here.
Negative
Negative
6.
6. Positive 7.
Negative 6, 5.
5.
5. 1,
Five.
2, 3,
5.
4, 5.
5.
5.
All right, so -6, 5. So even if you're not 100% sure that that was right, you can always plug it back in. So I'm going to plug it into the top one. So 5 equals -3 times -6 minus 13. So that's 18 minus 13, which is 5. So that worked. So it's not obviously exactly lined up, but it's close enough to approximate. That's why it says to kind of estimate, because sometimes it's hard to see, even on graph paper. All right, let's look at 12. We've got y equals 4x plus 3 and 20x minus 5y equals -15. So I need to change this one to get it in slope-intercept form. So -5y equals -20x minus 15. Divide by -5, so y is equal to 4x plus 3. Now, what do you notice?
It's just the same thing.
Yeah.
5.
This is the same as this. Okay, so what does that mean? If it's the same line, what option is it?
Infinite.
Yep, infinitely many solutions.
Oh,
Yeah, like how many solutions?
never mind. You want everything by 5, so that's why you. Okay.
So the first problems that we did had one solution. This has infinitely many. I don't see in the section where you actually are graphing them that there's a no solution one, but that would just be if they gave you parallel lines, if that should happen. So you don't need to graph this one because it was the same line. You can just say infinitely many solutions.
Why is it negative? Like, why is x positive? Everything else is negative.
Huh?
What? Because I divided by negative 5. Negative divided by negative is positive.
Sure.
Nate, what are you talking
My brain isn't back
All right. The next problems say to solve the system, then classify the system as consistent, independent, consistent, and dependent, or inconsistent. So, (18) 2x minus y equals 4, and x minus 2y equals negative 1. So I just need to basically get them in slope-intercept form and then see what's happening with them. So negative y is equal to negative 2x plus 4. So y is equal to 2x minus 4. And then on the other one, negative 2y equals negative x minus 1. Y equals 1/2 x plus 1/2. So these lines aren't the same line, and they don't have the same slope, so they can't be parallel lines. So my only option then is that it's going to have one solution, and so this is going to be consistent. Because remember, inconsistent is when there's no solution, and then independent is if it has only one solution. Dependent is infinitely many, so this is going to be independent. And so that's what you need to write for these, is like consistent, independent, consistent and dependent if it's infinitely many solutions, or inconsistent if it's no solution. So that's what I'll be looking for on those ones. If you have problems remembering which thing is which, independent is one solution, because if you're independent, you like to do things by yourself. Okay, so that's the only way I can ever keep up with it, being completely honest. Can't tell you how many years I've done these for, and that's the only way that I can remember. Let's see. 20. Got y equals 2x minus 1 and negative 6x plus 3y equals negative 3. All right, so the first one is already set up, so I just need to do the second one. So 3y equals 6x minus 3. Divide by 3. Y is equal to 2x minus 1. So what do you notice about these? So then what would my wording be?
Consistent and dependent.
Yep. Consistent and dependent. All right, and one more, and then unless y'all need to see more, we'll be done. 28. 5/2 x minus y equals negative 4. And 5x minus 2y equals 1/4. So negative y is equal to negative 5/2 x minus 4. So y is equal to 5/2 x plus 4. And then over here, negative 2y equals negative 5x plus 1/4. And then y would be equal to 5/2 x plus minus 1/8. So what do you notice about these? Same slope, which means they're what kind of lines? Parallel. So then my wording would be what? Inconsistent. So I will tell you in this section, that's really all you need to do, but you may want to get in the habit, because when we actually go to solving systems, like when you're given the two lines or two things and we're solving them the other way, like algebraically instead of, technically this is still graphically, even though we're not graphing them. With 20, you would have needed to write infinitely many solutions. Oh, I can't spell. And then with this one, you would have needed to write no solution. So a lot of times what happens when we get to the algebraic section of solving them by substitution and elimination is that people don't write that. And so then the assumption is that you don't know what the answer is or whatever, and you just stopped. So I would go ahead and get in the habit, even though you're not necessarily required to write it, of saying infinitely many solutions or no solution. If it doesn't give you one solution, I would say how many it has, or that it has none at all. So, only a couple problems because, you know, it is what it is. 3, 5, 17, 19, and 21.